Okay, so here we have the RS latch constructed out of two NOR gates and pull down system for the inputs. How is it pull down system? When the switch is open, this let's just consider one of that inputs, one of the inputs. So here's a resistor, 470 ohms, and the input to this top NOR gate here is connected to this point right here. So when the switch is open, the whole system is pulled down, so it rests at 0, and once we press the momentary switch, then for that moment of the switch being pressed, of course this system goes high. All right, so it's a pull down system because it rests down at 0. So RS latch, set and reset, RS SR. So here's the set input, and that corresponds with the Q, and there's a reset input that corresponds with the not Q, or the Q bar, or the Q not output. Okay, so here's the truth table. This is the schematic diagram for the RS latch. Basically what it is, there are two NOR gates, and one of the output of one is fed back to the input of the other one, and vice versa, crisscross. The output of the other one is fed back into the input of the first one, right? And then the remaining pins are going to serve as the actual controllable inputs. And for the RS latch, we have Q and not Q, or Q and Q bar as the inputs. Sometimes you're going to see, instead of the R, you're going to see the letter C, and that stands for clear. Okay, so sometimes it's a reset, a set pin and a clear pin, or set and reset, same thing. All right, but most of the time you're going to see RS or SR, set, S for set, R for reset. Okay, so here's the truth table. This is how it works. Here are the outputs, and I just arranged them in, the inputs, and I arranged them in a way that we can actually count using the binary system, just to kind of have some kind of a sequence that makes sense. So 0, 0, 1, 1, 0, 1, 1. These are all the possible combinations that we could have from the inputs. So let's just take a look at the second scenario here first. So we have S at 0 and R reset at 1. It is going to light up the not Q. Okay, and if we have the set at 1 high, or and of course and the reset at 0, then of course it thinks the situation is going to reverse on the output setting, and you're going to have the Q1, and not Q of course is going to be 0, as the designation suggests. Here's Q and here's not Q. So if this one is 1, this has to be 0, and if this one is 1, that has to be 0. It's just no other way that this device is supposed to work. Okay, so now there is that if you have both of them at 1, you're going to have SR, both of them at 1, then here is a situation that is not supposed to happen. Okay, so I'm just going to stop the simulation here. I'm going to place the text, place text, all right, and that is going to be in invalid situation right here. And can we make this thing red? Yes, we can. All right, let's make this thing in red and place it right here. That is an invalid situation. Red. Let's make it bold and red. Okay, so this is an invalid situation. Cannot have that, because if one is in one way, then the other one has to be the other way. There's no such thing as Q and not Q being at the same state at the same time. All right. So so that is an invalid situation. We are not supposed to have those two inputs. They should never go high. If If there is some circuit that makes both of them high, then it's going to be a wrong situation. Okay, so so we took care of that. Now there's that 0 0. If both of them are at 0, and this here it says latch, because it's a, well, SR latch, set reset latch. What does that mean? Well, the way we should look at this SR latch is that it is really supposed to rest at both of them 0, sitting at 0, both of the inputs sitting at 0. And then sometimes you're going to make one of them high, or sometimes you're going to make the other one high. Right? Now, when you momentarily make one of them high, the outputs end up being this way. Right? So when reset is at 1, then the outputs jump to the position of this state. And then if you release that 1 and make it 0 again, so you go back to the resting state, this one says latch, which means it's going to stay that way. Okay? Now, if you also then if you're still sitting at 0, and then for a split second you're going to make the other one high, then the outputs are going to have this state, that the Q is going to be 1 and not Q is going to be, of course, 0. So they're just going to reverse the situation here. And then, because it's a momentary situation, it goes back to 0. And what's a 0? 0 means latch. That means the previous state is being kept. So if you trigger one of the inputs and go back to go back home where it was, so step out, go home. Okay, step out, back home. All right. Something like that, if you can use that analogy there, then the whole device is going to stay that way. And then no matter how many times more you're going to press that one, nothing's going to happen. It's going to stay that way until, instead of that one momentarily, you're going to press the other one momentarily, and the outputs are going to go into this state right here. All right, so it's just click or click. Click one or click the other. Okay. So that's how we are supposed to understand this kind of a truth table. Okay, I'm going to zoom out a little bit. I have a circuit set up on the multisim, and I'm just going to press the simulation. I'm going to start the simulation here. Now, this is a multisim, so it's a software, and this thing is going to kind of go a little bit disorderly for a second until I push some button to make this thing settle down. All right, so here I press that, and this thing just goes nuts. So okay, press that. So okay, settle down. All right. Now, so this is basically what is going to happen when you turn this on. If you make the real circuit using real parts in the real world, they're not going to start blinking like that. Those outputs. It's unpredictable which one it is going to which state is going to end up as soon as you turn it on, if it's connected that way, unless you have some other circuitry to trigger it certain way, one way or the other. All right, so what did I say here? You press one momentarily and we're going to have one situation, or press the other one momentarily and we're going to have the reverse situation. Well, let's check it out. So now we have the Q, not Q, or the Q bar lit up. So let's just press momentarily. If we press the set, we're going to have the Q lit up according to this truth table. Let's see if that's true. Oh, look at that, it just happened. Okay, so and then how many more times I'm going to press that? Nothing is going to change. All right, then if I press until I press the other one momentarily, and so things are going to change in the reverse order. So so here's the thing, that if we can just press it for a very short time, why would we supply a clock that is longer? So if we're going to supply a clock, we're going to try to make it pulses instead of the whole square wave. Okay, we're going to talk about clock in the next coming videos. All right, so okay, let's press that momentarily, so the not Q should light up instead of that. All right. All right, here, okay, and these are just these indicators simulate a set and reset here. So I just put additional probes here. So here's set, reset, set. Okay, no matter how many times I press, or reset. and if I trigger one condition, the whole device is going to latch into that condition. It's going to stay that way. If I trigger the other condition, the whole device is going to latch or stay in the other condition. So that's pretty much the idea of a SR latch or RS latch. Now, just a little type of a little small reflection here. How is this happening? Why is it when I stop the simulation and press the simulation again, this thing goes out of control? Because this this software simulation, sometimes it's too ideal. Okay, it's based on calculations. Now, in the real life, there's no two things in the world that are the same. There is always something is different. There's no two things that are the same. So if you make two OR gates or two NOR gates or two whatever, they are not going to be the same. They're going to have little bit different propagation delays inside them. So one of them is going to race faster than the other, and the situation is going to settle down right away. Now, this is just too ideal. It's a software-based system. It's a software-based software. Okay, so so basically that's what it is. Now, so the little reflection is that it happens. This whole situation that we can create here with pressing R and S and triggering Q or latching into not Q or Q, it happens because propagation delay exists. You know, propagation delay slows things down. So sometimes we're not getting things done as fast as we want to from one place to another as far as signal, but in some cases it actually works for us. Just think about it. If you have one certain condition and you can get a pencil and draw it on a piece of paper with pencil and just write the ones and zeros, so you just go 0 and 1, and then based on the truth table of a NOR gate, you can just you can come up with the condition of one of them, and then you can follow that into the condition to this one, and those two are going to give you that input, and these two, ones and 0, are going to give you the other input. Okay, so because when you change that over here and nothing changes here, so that gate is being triggered quicker, and then the condition changes and that one follows. And then if you trigger that one momentarily, then this gate is being triggered first, and that signal travels through the circuitry, whatever else, and that gate is going to follow. So propagation delay actually makes it possible for this device to exist in real life.